Hey, welcome back to Fan Mama Physics! In this video, we're going to do examples in 6.1, but vertical circles. So here, take a look at the vertical circles. This is part 2 of 6.1, and this is example 1 with a skateboarder going around in a loop-the-loop. So if you're not sure what that is essentially, imagine a skater going down on the bottom, and then catching some wind, going around this loop-the-loop, and making all the way around and coming back down through the bottom again. Very tough maneuver, and if you're thinking you need a very high speed for that, absolutely. You definitely need a very high speed for that in order for you to clear the loop-the-loop. Okay, otherwise it'll be tricky. Ooh, I have to bring that to class. Okay, so, well then, let's take a look at what this question is asking us. A 75 kilogram skateboarder is trying to clear a loop-the-loop with a radius of 3 meters. So some labeling over here, and clearing means that he needs enough speed so he's able to clear the top without falling down. And if you go too slow, you can't make it over the top. So we're trying to figure out how that can be done. So here the radius, I'm just going to label there, is 3 meters. What is the minimum speed of the object, which we assume is a skateboarder, at the top of the loop-to-loop? Okay, so that's this guy over here, which he's going to stand upside down, okay, and on the skateboard, like that. He needs enough speed to go over the top. Usually the question is, what will be the minimum speed? Because if he goes faster than the minimum speed, of course he's going to be able to clear the top. So how do we do that? First of all, let's draw a free body diagram acting on this guy. We know that the force due to gravity is going to act down. Oh, interesting. We've never had a case where someone's upside down in which the force of gravity is not actually like hitting another surface. And so there's that. However, there are some other forces acting on him as well. What will be the other one? First of all, his skateboard is touching the floor. The floor is not on the it's not on the bottom. It's on the top now. So, in fact, you might think that the normal force is going to act upwards like this. Okay? That's wrong. The normal force doesn't point up because the skateboarder isn't standing on top of the loop-the-loop. He's inside the loop-the-loop, in which he's kind of butting heads against it at the top. So the normal force acting on the skateboard, the normal force, is actually pointing down. Well then, isn't that interesting? So you have both forces pointing down towards the center of the circle. So then how do we figure out the minimum speed? Because it looks like we're given the mass, we're given the radius, we're not given anything else. We're not given the normal force or anything. So this takes a little bit of thinking involved for calculating the minimum speed. We know that in order for this guy to have a really, really large speed, so imagine, let's think from the other side. If the skateboard was going really fast, that means he's going to need a stronger force to keep him moving in the circle. And if you want to look at it mathematically, it looks like this. We know that F net is equal to AC, which is centripetal acceleration, which we know is V squared over R. So if you take a look at V, if V is very high, if V has a large speed, he's going to need a stronger F net pointing towards the middle of the circle, meaning he's going to need these forces to be very large. Okay? Now let's start to move towards the other end of the spectrum, okay? In which he's moving very, very, very fast. And for him to move very, 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 very slow, he doesn't need as much force directed to the center of the circle. So we're going to minimize. So we want to minimize, I can't spell, minimize Fn and Fg, okay? Well, here's the thing. Can we minimize Fg, the force of gravity acting on the skateboard? You're right, we can't minimize that. His Fg is always the same. As long as he's on the surface of the Earth, his Fg doesn't change. So this cannot change. We're stuck with that. Okay. Well, let's think about the normal force. Okay. And if you can't think of it in terms of the the skater board touching the top. Let's just say a normal object not touching in contact with any other object. Let's say my hand on the table. I'm going to experience a normal force. How much normal force I experience is going to depend on how much applied force, how much I push down on the table. So my Fn doesn't have a set value. It can change depending on the my opposing force due to Newton's third law. As for the skateboarder, as he's clearing the top, his normal force can range from anywhere from 0 all the way to however much his knees can tolerate, really. If he can't tolerate with his knees, then he's going to crash and burn at the top, which is not really fun. But his normal force can be 0. It's just like my hand on the table. I can lightly touch the table. I can barely touch the table. I can pretty much just have my hand just skimming the top of the table, and I'll have a normal force of 0. The skateboarder can also have a normal force of 0. So in fact, the minimum value for Fn in this case is 0. So that is the key to answering this question, is to realize that the only way to minimize Fg and Fn is to have Fn be 0. You can't make Fg any smaller than Fg. So let's see what happens now that we don't have Fn. And I'm going to write this note here. For us to find the minimum speed, we know Fn must be 0. So our net equation is now reduced to Fg, which is providing the centripetal acceleration, and that's going to be equal to the mass times AC, which is centripetal acceleration, which I'm just going to write v squared over r. Okay? Well, let's work on this a little bit, because we know that Fg is just mg, so then we can simplify this. So let me erase this guy over here. So we can simplify this to be mg is equal to m times v squared over r. Hey, guess what? The mass also cancels out. Bam, bam. What do we want to find? We want to find the minimum speed at the top. So that's just v over here. So let's solve for v. To do that, we're going to multiply both sides by r, like this. So this r here goes away. We are left with r v squared is equal to rg. And to solve for the v, we just have to take the square root of both sides. We then get the square root of rg. Radius is just 3 meters. And the acceleration due to gravity is just 9.81 meters per second squared. We put that into our calculator, 3 times 9.81, and then take the square root, 5.42. 5.42, which is going to round to 5.4 meters per second. Okay, so that's the minimum speed that this skateboarder will need to have at the very top in order for him to be able to clear it. If he has anything less than that, then that means the Fg is going to be too much. So the force due to gravity will not be able to will cause him to fall down. Okay, he will not have enough speed to kind of escape or to leave the influence of gravity as he's traveling around the circle. Okay, all right. So that is A. A is tricky. B is also very tricky too. So let's just be careful. What is the maximum normal force that the skateboarder will feel, assuming he just cleared the top of the loop? So in this case, when we say he's assuming he just cleared the top of the loop, meaning that we're going to use piggyback on what we did for A, because if he just cleared the loop, that just means he used the lowest possible speed to clear the top. So we're going to use the fact that he started at the top, going through the top at 5.4 meters per second. Now, where is this guy going to feel the largest normal force? We know that at the top, he's going to feel no normal force due to the minimum speed. But as he is coming down to the bottom of the circle, First of all, let's just use my arrows here, use my mouse. As he comes down, he's going to gain speed. Remember, this becomes part of it becomes an energy problem because as he comes down, some of his potential energy will be converted into kinetic energy, which means his largest possible speed that he will have is going to be at the bottom of the circle. So the top is an interesting place. The bottom of the circle is also very interesting. We'll probably have to draw a free body diagram for that as well. So let's just let's just do that. Maybe, I'm going to use this circle over here to model that. So imagine he's at the very bottom, okay? And, oops. Which means that the force acting on him would still be Fg in this case. But wait a minute. There is a normal force, but in this case, the skateboard is on the ground, which means normal force will be directed upwards. And look at this case. The normal force is directed towards the center of the circle, while Fg is directed away from the center of the circle. So this becomes interesting. It's almost as if the person has a larger Fg, he's going to experience a larger Fn. It's going to be a lot harder for him to stay in the circle. So if I have to write the Fnet equation for this one, it will look like this. His Fnet towards the center of the circle is going to be Fn. Remember, when we talk about circles, it's always the direction, all of the forces directed towards the direction of acceleration minus all the forces opposing the direction of acceleration. Since the acceleration is towards the center of the circle, Fn is positive, Fg points opposite, it is negative. Okay, and this is equal to the mass times the velocity, tangent velocity squared over the radius. Whew! All right. So this bottom, it's almost as if the direct opposite of the top. If anywhere in between, as he's falling through the circle, his normal force is still directed at an angle. He will not get the full-blown Fn until he reaches the bottom. So it's the bottom that he's going to experience the largest normal force, in which not only Fn has to keep his weight, but also has to keep this person moving around in that circle. And as you watch some videos, maybe you might notice that the skateboarder, the first time that they bail is at the top because they can't make it over. The second time that they bail is at the bottom because why? Their knees cannot sustain the impact or the normal force that they need to exert in order to clear the bottom. So Fn is very large at the bottom, the maximum at the bottom. Okay, so to solve for F, now we want to know what Fn is. We got to solve this one. We got to move Fg to the other side. So we're going to have to plus Fg over here, plus Mg over here. We're going to get Fn is going to be mass times velocity, tangential velocity divided by r plus mg. Well, we're almost there. You might think, yeah, we just plug in this radius and the mass, the gravity, and we plug in that tangential velocity, right? Think again. Because as he's coming down, remember what I said earlier, his potential energy is getting converted into kinetic, meaning he's going to gain more speed as he is coming down. Which means this v value, this speed, is going to be larger than 5.4. We need to calculate this v now that he has made it down to the bottom. So this becomes an energy problem where we have to kind of calculate his speed at the bottom. Then to do that, we're going to use a bit of energy that we learned in a previous unit. So with mechanical energy, we know that the I'm going to do it over here, okay? I'm going to do it here on the bottom in case I need more space up there. We know that the mechanical energy, Ki, plus EP, initial potential energy, is equal to his final kinetic energy plus his final potential energy. So to find his, to find the speed, we need to identify a few things. First of all, we're going to set the initial to be the top of the circle, the final to be at the bottom of the circle. Top of the circle, he has some kinetic energy. He also has some potential energy, but at the very bottom, he's not going to have any potential energy because he's no longer some height above the ground. And so we put our equations in here for kinetic energy, which is 1/2 mv squared, and this is going to be his initial velocity squared, plus mgh, in which the height will be, oh, careful. The height is not just the radius circle, it's 2 times the radius circle because it's the full diameter of the circle that he is above. And this is going to be 1/2 mv final squared. I'm going to be able to cancel out the m's in this case, and I'm going to have to assume that no energy is lost due to friction or anything else as he is coming down. Of course, that's not the case, but to make things a little bit simple, we kind of have to do that. Well then, so we have this, we have this equation here, and we're going to have to solve for this v first, okay? So if I have to solve for this v, we gotta first multiply everything by 2 to get rid of the half, okay? So that's gonna be v is equal to, this is kind of ugly. Oh, don't forget, it is v squared. 2 times a half, that's just mu squared, plus 2 times gh is just 2gh. And then don't forget, the last thing is the square, taking the square root of both sides, meaning this is going to be, okay, oh shoot, I forgot, there is no mass here, you're right, there is no mass, because the mass here got cancelled out, all the masses got cancelled out, so there's no mass here. So it's just initial velocity plus 2gh, kind of looks like kinematics, doesn't it? So his initial, okay, is going to, oh, don't forget the square root. His initial is 5.4 ... We don't round anything. Squared plus 2 times 9.81, which is gravity. And the height, which is not 3 meters, it's 6 meters for the total height. Okay, and so we put that into our calculator. We get 12.13. 12.13 ... meters per second. So that is the speed that the skateboarder will have at the bottom of the circle because the potential energy that he had will be converted to kinetic energy. Okay, so now we can go ahead and solve this. All right, so his mass, we have 75 kilos, okay, and his speed at the bottom is what we just calculated, 12.13, no rounding, okay, ... This is going to be squared, divided by the radius. Now we can use just the radius, which is 3 meters, plus 75 kilograms times the gravity, 9.81 meters per second squared. And this is going to give us, this is going to give us something, times 75 divided by 3 plus 75 times 9.81. Okay, 4,414.5 newtons, which we will round to 4400 newtons. Wow, what a problem. Okay. So, there you go. This is example 1 from vertical circles. The key thing to note in vertical circles is now that you have forces, we will have forces that point along the direction of acceleration, not just towards the center, but also away from the center, depending on which part of the circle you are talking about. Because in the vertical direction, we have a little bit more forces, such as the normal force, such as especially the force due to gravity, since that's pointed towards the center of the Earth, okay? So vertical circles, here we go, first example. Thank you for watching. There's more coming your way. Good luck, Fat Mama Physics, signing out.